Hey you guys, welcome back to the channel PHYSICSSIRJEE, and here we are in PHYSICSSIRJEE Originals. As I promised you in the last video on topic of EMI, that we would be taking up the continuation of the reading of voltmeters. So the last video was all about reading of voltmeter in a motional EMF problem. This is going to be covering the idea of potential differences and voltmeter readings in time varying magnetic field. Okay, right? So in case you are new to this channel and new to this video, please do make sure that you continue watching this video only after watching the video that you see on the screen, the thumbnail of which I have put up. It's a must watch in case you want to understand the reading of voltmeter ideas. And there was a very decent elaborate discussion that I did in that resolved series video. So link is in the description below. Please do watch it and then come back to this video. Okay, so I have divided this particular video into 4 passages or 4 comprehensions, followed by 3 to 4 questions each, so that we can do the complete postmortem of the concept. Okay, so let's start with the passage number 1. So here it is. In the case 1, as I call it as passage 1 or case 1, you could clearly see that there is a cylindrical region of time varying magnetic field, and in that cylindrical region which is going into the board, the B is varying in such a way that pi r square into dB by dt is equal to 12 volt. Okay, so the rate of change of flux is 12 volt and dB by dt is a positive number. Okay, so this inward flux is increasing with time. A and B are 2 space points, and there are 3 questions that he has given. One about the induced EMF along AB. The second one is the potential difference along AB, and ideal voltmeter if connected between space points A and B, right? These 3 sides are dotted lines. There is no material there. Then what would it read? Okay, so you want to give it a try. You can pause here and then do the problem. And you want to do all 4 passages at a go. I have pasted the entire PDF of these 4 passages in the description below, so you can try it all the 4 passages all together and then come back to the video. Okay, so I'm going ahead with the concept description first. So you should be knowing, so I'm not taking any chances, just to explain a brief idea about the concept of non-conservative electric field produced by a time varying magnetic field. Okay, so on the right side there is a picture of whatever was given to us. There is a cylindrical region which I have represented in the blue color. Can you follow the right side diagram here? Okay, so in this region, the cylindrical region of radius r and uniform non-constant magnetic field that is present in this particular idea, right? Um, there can be 2 loops of travel that I can think of. Okay, so this red colored path inside is a path for inside points where I want to ascertain what's the non-conservative electric field, and also outside points, as you could see, are path for the in the green color I have drawn. Okay, so let's go on to this side. So EMF calculation can be within these particular regions done in 2 ways. Okay, so EMF in a particular closed loop of path is a path integral. E star is a symbol that I use for extraneous field or a non-conservative electric field. Capital E is usually used for conservative electric field. Okay, so that's the standard rule. So a closed loop integral of non-conservative field actually gives rise to the EMF, right? If this was conservative, this value should have been 0, but here it won't be. Okay, and on the other side, you can also calculate it using Faraday's law as the rate of change of flux. Okay, so pi r square, let's say, is the area of the path that I'm using on the right side, either the red colored or the green color path. It should be the pi r square into dB by dt. I'm writing dB by dt as v dot. Okay, so for points inside, which is the red path where small r is less than this blue color capital R, please understand this capital R is the field boundary region, magnetic field boundary region. Outside magnetic field is 0. Okay, so that for that, this one will become E star into 2 pi r, whereas the right hand side will become pi r square into b dot. Therefore E star inside comes out to be r by 2 b dot. Okay, and all these field lines would be tangential to that path. Okay, for points outside, which is the green path, you go around, the left hand side would be still E star into 2 pi r, but for right hand side you should be very careful. You cannot actually write the entire pi small r square this time, because small r is greater than capital R, because magnetic flux would be confined to only this much cylindrical region. So there's a small change here. Here it should be pi capital R square, and then you would end up getting a decreasing field outside as you walk away from the region. But you should understand that magnetic field may exist only inside the cylindrical region, but electric field, non-conservative one, that is a circular loop kind of one, will exist both inside and outside, and the formulae are given in this format. And very importantly, direction of these electric fields are tangential in direction. Okay, right? So very important. With this concept, I just wanted to give you a picture of how these field lines will look like. So in the diagram A, as you could see on the left side of your screen on the top, the field lines are, as you could see, in the tangential direction that we discussed. Okay, right? And if I place a conducting loop, then this electric field, that E star field, is going to drive a current. If I place a material will contain free electrons, and then therefore there would be some current that would be induced. And in another view, that means the side-on view, that field lines will look like this. You could see the B bar lines are like this, then E bar induced lines would be circular like this. Okay, and in the same way, you can see in the right side picture that I picked from one of the standard engineering textbooks, if this cylindrical region, you might be feeling how it can be created. It can be attributed to a solenoid cylindrical region. Inside the solenoid only magnetic field will exist, and it fits, let's say, a time varying one. You could say a non-conservative field will loop around even outside also. So even outside, how do scientists or physicists knew about this? They placed a material outside and they saw current flowing, and they said, okay, fine, if the current had to flow outside, then there should be a non-conservative electric field. The same thing viewed along axial direction, you could see the metal ring for the outside path also will have non-conservative electric field, which in that textbook he calls it as non-Coulomb electric field. So multiple names. You can call it non-conservative, you can call it non-Coulomb, you can call it extraneous. I will call it E star. Okay, right? So let's move ahead with the passage again. So this is the passage. So we'll go one by one. So the region is such that the AB line subtends an angle 60 degrees at the center, but the AB is outside. Okay, so this point is outside point. So first, let's go to the case one, which I'll do elaborately, and then we'll quickly go. Okay, so in case one, if you correspondingly draw the same picture that I gave in the question, you would realize that the induced AMF along AB means integration of E star dot DL, right? Then I need not talk about a closed path. So this is small error here. Yeah. So that is normal integration. Closed loop need not be done because I have to travel only from A to B in this question. Okay. So this is what induced EMF can be calculated as. But it is tedious. Why is it tedious? Because when I try to travel along this AB line, then the electric field would be perpendicular to the line joining the center to this. Remember the tangential field lines? So E stars won't be along this green line. So if I were to perform this integration, I should have taken the dot products of these E bars dot DLs, and that angles will keep changing, magnitudes will keep changing, making it very difficult. I'm not saying impossible, but the doing of integration should be avoided. Alternatively, you can take the closed path always with radial lines. Our job was to calculate from A to B only. Remember, this is just a path. This green line is not material, just a path, not a wire. Okay. So always the idea is, if any path is given, complete that path using radial lines. Why radial lines? Because when you go along these radial lines, along this line, the E star will be perpendicular to that. Remember, tangential direction, right? So closer positions you will have greater fields, and farther positions you have diminishing fields, but whatever they are, I think they are perpendicular to this path. So when I do that E bar dot DL throughout the loop, I'll end up getting only E bar dot DL on this line. So that should be equal to the Faraday's law flux rate, right? Flux rate will enclose only this much area, right? Why is this much area? Because it's not because I like the cylinder, it's because only magnetic flux is there inside this cylinder. There is no magnetic fields here. Okay, so the value of this integration would be on two counts. One is that the field here is normal and field only exists here, giving you the dot product, is equal to the area of the shaded region that I put in the white into dB by dt. Since this is 60 degree, remember the overall area into dB by dt was given as 12 volt to us. Therefore, this is 1/6 of that area of the circle. So the answer should come out to be 2 volts. So this is a nice genius way of calculating the electric EMF along a particular path. I think now you realize that even if I had given a path which is outside and going like this from A to B, right? If I had gone like this, can you see on the right side I have to put a diagram? So as long as these two lines, then EMF along this line also would be the same. Okay, provided the path is outside. Okay, so that's like something that you can take out from this question. So this is the problem number 1. Let's go to problem number 2, which he asked as potential difference. So here I have put the problem again. Second part of the question was potential difference VA minus VB. Now there is no material, this is just path, and there is no conservative field here. It's only E star that is there, right? Remember, potential difference as a definition is only related to the path integral of conservative electric field. No conservative field, no path integral, so answer should be 0. So the answer to the second question is 0, and answer to the first question that we got, let me mark it off, was 2 volt. Okay, so let's move on to the third question. An ideal voltmeter, if connected, so this is the third question, ideal voltmeter, if it is connected across this, even the question is laughing at us. Okay, so it's just smiling that you're connecting an ideal voltmeter in space just like that. I think in the previous video itself I told you a voltmeter will deflect only if current passes through it, however feeble it is. Small current also, it should be non-zero current. If current doesn't pass through a voltmeter, it can't read anything. Okay, so the value of the reading should be 0 because there is no current as it's an open circuit. So it's obvious that this answer is also 0. So let's move forward to the case 2. So this is the second comprehension, right? This is the first page of it, and because it was not fitting in the same page, you can pause here, read the question, solve, and then move ahead. And this is the third and fourth. So it's a comprehension followed by 4 questions. Okay, right? So let me read through the questions. It is same as case 1, same conditions and all. Diagram I am not drawn. This is same 60-degree logic, everything, but only difference is last time all these were dotted lines. Now instead of AB being a dotted path, just a path, this time I placed a metal rod. Metal rod is of 0 resistance, which is placed along AB. Again, I want what is the induced EMF along AB, path difference, potential difference across AB points, and if a voltmeter is connected across AB, now there is a rod, right? So if it is connected, does it read anything? And if so, what among these options? And the fourth question is also interesting, where we try to rotate this loop of the voltmeter up, right? Imagine the rod is kept like that, and it's like a hinge or a axis about which this voltmeter is rotated out of the page, and the plane of that AB will be perpendicular to the page, let's suppose. Does the reading change? Okay, so these are the 4 questions. Have a try and then move ahead with the solution that I'm going to provide. We'll do question by question. Okay, so let's start with the first one. We'll go with the first one. First one is pretty simple. I think EMF induced is related to the E stars, and whether path is there or material is there or material is not there. Remember, E star already exists from between A and B. So answer to the first question in the previous case should be the answer here also. So I need not even separately write, it should be 2 volt. Okay, right. Then going to the second question, this is even more interesting. So you should realize that in this particular problem, he's talking about the potential difference. Okay, so last time we rejected potential difference when the material was not there because there was no electric field. One thing's for sure, an open rod like this, can you see I've placed the rod here? Just follow the diagram, follow my lead. A lot of things are in the board, so just follow me. So if this is AB, I realize one very important thing, that any open rod like open voltmeter cannot have a current passing through it. So there is no flow of electrons here. Moving charges are not there. Okay, so free electrons are available because it's metal, but moving charges are not there, right? Charges are at rest. So which means in this particular point, there will be an electric field E star, like I said in the first question itself, which is perpendicular to line joining like this. If I zoom that into that material, so this is the zoom version of that material, the E star will be like this. This is all material thickness. Okay, right. Since the charges here should not move, they should rearrange themselves in such a way that they produce an electrostatic field, a conservative one, exactly anti-parallel to it. This is what we learn in electrostatics. Inside a conductor, net field should be 0, not electric field, but net field should be 0. So here, the good thing is there will be a conservative electric field generated, which will try to counter E star, not just here, at every place. So new positions, if you go, whatever is E star there, E will adjust itself to cancel it. Which means as I now manipulate this diagram, this E's component along the rod, can I call it as E component like this? So this green one will definitely have a component along the rod. And when I travel from A to B, now trying to integrate the conservative electric field, this EC will produce a value. Okay, right. So for a free electron inside, can I write J equal to sigma E, where this time E is combination of both these two, and sum of these two is 0. So the value of J is 0 and I is an open rod. So these two should be opposite. So component of E bar along the rod EC decides the potential difference, and its dot product should be equal to the dot product of E star along the same rod, which we already found out as induced EMF, which is interesting. That value was 2 volt and this value also should be 2 volt. Only difference is the EC is pointing from B to A, as you could see. Okay, so always conservative electric fields point from higher potential to lower potential. Therefore VB minus VA should be 2 volt and not VA minus VB. So I wantedly gave a wrong question here, because if I ask you VA minus VB and among the 4 options, none of the options are strictly right. Okay, right. So all the 4 are wrong. The answer, exactly speaking, is minus 2 volt. Okay, right. A wrong question wantedly given so that you should be able to adjust your concept there. Okay, so VB minus VA, direction of EC is towards always lower potential. Okay, so A is the lower potential compared to B. I hope you got the point up till here. So let's move on to, this is a very interesting concept that you need to understand, that there is electric field existing. You should be able to realize that this E value will exist outside also, because these charges produce this electric field even outside. Think about it. We'll discuss it in next video. Next. Case 2 continued. When then that metal rod, we place a voltmeter and we want to read something. Last time we complained that there will not be any reading because there was no material and the voltmeter was just hanging in midair. Okay, this time let's see what can happen. So there are 2 ways of looking at this. Method 1, as I told you in the previous video itself, how to look at the voltmeter readings. So in method 1, in the isolated loop of this voltmeter, this just entire loop, if I go, the value of magnetic flux is 0. Do you see any magnetic field here? Magnetic field is here, it's not here. So the value of phi b is 0, therefore rate of change of flux is 0, which means the total EMF in that is 0. So current is 0, which means the reading has to be nil. Okay, simple. If current doesn't flow, then voltmeter won't read anything. Current has to at least tend to 0 in an ideal voltmeter. Tending to 0, equal to 0, or different. So that itself should tell you that it is 0. If you want to validate why it is 0 in EMF format, we already saw that this A to B has a induced EMF in this direction. Remember, potential difference was this way, but induced EMF is this way. We saw that E star integration, but same kind of thing will also have along this path. Remember, I told you along any path you should get the same induced EMF. These 2 batteries fight with each other in that loop, and therefore current is 0, and therefore there won't be any reading. Remember, this connecting wire also will have material inside that, and there would be conservative fields and non-conservative fields that would be available. So either which way, you should realize the answer is 0 for this. Coming to the 4th question, where we rotate this thing, right? I remember that we have to rotate this so that the plane of this loop is perpendicular to the reader. I think by now you should realize, even in that configuration, the magnetic flux would be 0, and therefore in this particular problem the reading would be 0. It would be even more interesting if the rotation is done in a 180-degree format, that so that the loop is like this. Okay, so maybe you can think then the reading will change. Okay, so maybe we'll try to take it up in the next videos. Okay, so that was the 4th one. So 4th one answer is also 0. So let me mark all answers here itself. So 2 volt I got. The second one, no answer. All the 4 were wrong, and I ended up getting minus 2 volt for this. The third one was a 0, no current, and even in this one it is a 0. Okay, so 2 passages done. Let's move on to the 3rd passage. So this is the case 3 or passage 3. Repeat all case 2 questions, but this time the metal rod is not 0 resistance but a finite resistance. Last time metal rod was having 0 resistance, but voltmeter is still ideal. Okay, I think by now you should realize that all the situations would be similar. Whether the rod has resistance or not, it matters only when current is flowing. Once the rod is an open one, its resistance there or resistance is not there shouldn't matter at all. Okay, so I hope you realize that. And all the 4 cases, answer for the 3rd one, resistance, you could see at the bottom I'm writing, resistance becomes important only if there is a current. Okay, so the answers for the third passage, this was a very straightforward passage once you get the original value. So this is 2 volt, and VA minus VB all are wrong, and you end up getting minus 2 volt. Okay, and ideal voltmeter is connected to A and B, then the reading would be 0. There won't be any current flowing through that. And even here the phi b will be 0, and therefore phi b dot is 0, I is 0, therefore no reading for the fourth question too. So 3 passages is done. So second and third were just twins of each other. Okay, so fourth one, let's see, let's make it more exciting. Now what I do is, apart from the rod, I place even material rods like this. So now I have closed a loop with a material. Okay, right? So now a loop is completed with 3 metal rods of each resistance R. So this is R, this is R resistance, and this is R resistance. And take value of small r equal to 1 ohm. Okay, and same old idea of pi r square dB by dt of this is 12 volt. Okay, right. So induced EMF along AB magnitude, that's first question. Potential difference VA minus VB. I tried my best to give as many options as possible to solidify our concept. Okay, so whichever of these matches we'll try. And then the third question is about an ideal voltmeter connected across this. Now you could see all of this is a metal loop. Current could be flowing in this. And then when you connect a voltmeter, what does it read? Okay, so these are the 3 questions in this particular problem. Okay, so you want to give a try, have a try, and then I'll move forward with the solution. This would be even more conceptually exciting. Okay, so let's see the first one. I think first one by now you should realize is the same answer every time, whether it is a free space, whether it is having a material, whether it has resistance, zero resistance. It's induced EMF is always about integration of E star, that is non-conservative field. Remember one thing, even before you place this material loop, non-conservative electric field existed there. So its integration always will be the same. The conservative electric field comes into picture once the material is put. Okay, so that will change the answer. So the first one across all 4 problems, I think by now you should realize is 2 volt. Okay, right? Now coming to the potential difference, I hope there is a change. So let's go to that part. So this is the second problem. I pasted it again. I want VA minus VB. Now what I realize is, you could see on the right side in the picture, I'm depicting the entire diagram. Can you see a 2 volt I have placed here? That is because A to B, it's like having an induced EMF of 2 volt. I mark the first answer. I can visualize it in my mind as a battery. Actually, the battery would be a distributed battery everywhere. So throughout this integration, I am placing it here without loss of generality. Also, I know that the entire part resistance is this 1 ohm, and therefore I can consider this as a non-ideal cell. Whereas this one and this one, can you carefully observe, even though there are materials, I didn't place a battery there. You remember that electric field, non-conservative one, will be perpendicular to these lines and therefore will not induce any batteries in this. Therefore, there will not be any batteries, but they'll play a role in the current. Okay. So with this loop, the total EMF driving the current in the loop is 2 volt. We have already seen that's all related to this area enclosed and all that. And all of this EMF would be along AB only. Please remember, Faraday's law gives you the total EMF always. It will never give you the location of the battery. That's the limitation of Faraday's law. Whereas the concept of applying Maxwell's equations and integral E bar dot dl equal to pi r square dB by dt gives you the location also, because we found the value of E star in the first conceptual slide. Okay, E star is outside r square by 2r dB by dt. So we know the location also. Okay, so what's the value of current driven in this particular loop? 2 volt driving 3 series resistances, 3 ohm would be 2 by 3 ampere. So nicely 2 by 3 ampere would be flowing in anti-clockwise sense because inward flux is increasing. We all know that. Okay. Now I will travel from A to B, use nice Kirchhoff's law from A to B to get the value of VA minus VB. So how do you start? You start here, go this way, VA plus 2 minus 2/3 current into 1 ohm equal to VB. Rearrange, you get VA minus VB equal to minus 4 by 3 volt. So among these many looking options, the answer is going to be minus 4 by 3 volt. With sign you have to write. Okay, so that's the second question. So the third question, it becomes even more interesting. If I were to connect a voltmeter across A and B, does it read the potential difference across A and B? A and B potential difference, we got 4 by 3, right? So if I connect a voltmeter across A and B, does it read 4 by 3? You want to still give it a try, pause, try and then come back. Okay, so this is the last question of our video. So let's see. An ideal voltmeter is connected across AB and in the same plane as the page reads how much. You see, I have given 4 by 3 also. Let's check whether it's correct or not. So the placement of voltmeter of a very large resistance, that is ideal voltmeter, its large resistance draws very small current. Remember, already current is flowing in this loop in the upper triangle. So connecting a voltmeter here, which is having a very large resistance, yes, it does draw a current, but it's a very small current. That current is needed for its reading, but it won't alter significantly any of the value in this particular loop is what he's trying to tell. So it doesn't change the main current appreciably. Okay, while writing values, I can write the main current as I itself. Okay, but IV will be there. IV tends to 0 in this problem. Okay, so in this particular loop, which I will draw again here, see this loop I have drawn here, A to B, we have all agreed that it's like a resistance and a cell of 2 volt. And this voltmeter will also have a battery of its own and will have a 2 volt. Remember that we did even in the other problems also. And there is a resistance of the voltmeter also. Now I am saying that there will be a current that will be drawn by this voltmeter, and I'm writing it as some IV value. Okay, right. So in this particular problem, the direction of IV doesn't matter. It could be actually even like this also. Okay, right. So when I go in the loop in this sense, again I do the same thing, minus IR plus E1 minus I2 plus or minus, it doesn't matter, IVRV, its magnitude I want is the reading. Okay, so is equal to 0. And we know these two batteries are of equal value. So these two is 0, because even when you connect it like this, I think inside this loop, Faraday's law tells you total EMF should be 0. Remember, these are EMF terms. Okay, so this combination is 0 as phi b dot is 0. So the value of reading, we don't know IV value. Remember, it tends to 0. Value of RV is also not known, but it tends to infinity. But in the last video, I told you the product tends to a finite value, and that finite value indirectly you can calculate as IR. And IR is not the previous answer. Previous answer was 4 by 3, answer is 2 by 3 volts. So the reading is different again from the potential difference across the voltmeter. Okay, so this would be the required answer there. Okay, so now with this kind of a practice, I think you can next solve with confidence. Whether you have solved this before or not, it doesn't matter now. I think with confidence you can solve this Pathfinder objective question. I think in the after last video also, emotional EMF, I have given a practice problem for Pathfinder. That was the objective number 1. This is objective number 3. What I'll do is I'll make a combined video of these two problems in a Pathfinder series coming up. Okay, apart from that, within a week time, I'll give you AITS select series, in which a collection of the problems on EMI and voltmeter practice will be done. There the questions would be slightly more typical than what we have seen. The ones that I've covered here are basic concepts, and they have a better chance of coming in the JEE exams, whereas AITS select questions will have slightly tougher, but it will improve our concept. So we'll try to take up that as a collection in the next AITS select series. Okay, so I hope you like this originals video. My endeavor, my effort was to collect all the concepts in one particular problem, and whenever this video is done in a proper manner by a student going through it, I think all his conceptual doubts get answered in this particular topic. So apart from that, the other series are there. You can check them out, and the links of all the playlists are in the description below. Please make sure you go through them, right? And please do like, share, and subscribe to my channel. And in case you have liked the video, please do press the like button immediately. It will help me in pushing the channel. The YouTube algorithm recognizes the number of likes in a video and then recommends it to the rest of the people. So in case you're sharing, you share only to finite people. I think the YouTube algorithm, once it checks the number of likes, it will keep going to many unknown persons. Okay, so I hope you do understand and do like the video. So, and please stay with me, and thanks for your company. See you in the next video.